In the beginning, God created the heaven and the earth. And the earth was without form and void, and darkness was upon the face of the deep. And the Spirit of God moved upon the face of the waters. And God said, "Let there be light." And there was light.
All right, tonight we're going to continue our theme on the concept of the fine-tuning of the universe and of our solar system. Why is that important, or is it important? Is there, the question I have to you guys out there is, what's the significance, if any, of a fine-tuning of the universe? Is there? Is the fact that our youth is fine-tuned have any bearing to Bible evidences? Because that's what this class is. I mean, when you see the fine-tuning, and we did this in our study on evolution. We looked at the human body, we looked at life, how intricate and detailed DNA was, and how there had to be a designer there. It's the same thing, but now we're looking at the universe. Now, next week, we'll get into science answer to that. What does that mean? But this is a quote from Robert Collins. It comes from a book called The Case for Our Creator by Lee Strobel. Lee Strobel's written a lot of books. He's got one, A Case for Christ, and I forget, A Case for Life or something. But anyway, he's got several books on the market. It's a very good book. He interviews some of the people we've been talking about in this class. And this comes from Robert Collins. And he says, over the past 30 years or so, scientists have discovered that just about everything about the basic structure of the universe is balanced on a razor's edge for the life to exist. I like that expression, on a razor's edge. It is so fine-tuned, it's to a razor's edge. And he says that the coincidences are far too fantastic to attribute this to mere chance or to claim that it needs no explanation at all. And I agree with that. I mean, the coincidences, in my opinion, are just far, far too great for all of this to have come about by chance. And the fine-tuning of the universe, we're talking about the fine-tuning in the universe so that there can be life. If you had a universe there was no life, there'd be nobody to know about the universe, right? So the universe had to be fine-tuned to a point where it would be able to support life. So when we're talking about the fine-tuning, that's what we're talking about, so that there could be life on Earth. Also, this comes from Paul Davies, from his book, The Mind of God. Paul Davies, a very good writer. And he says the fine-tuning of the universe provides prima facie evidence of deistic design, just like David was just mentioned. It is basically, that's the evidence that we have, that there is a designer in the universe. And that's what the book of Romans talks about, Romans 1:20, which we'll mention later on in this class. And then also from Robert Groves and George Stanchuy from A New Story of Science. A universe aiming at the production of man implies a man directing it, because that's what it seems. It seems like the universe is aiming at the production of man implies a mind directing it. And though man is not at the physical center of the universe, he appears to be the center for its purpose. There seems to be a purpose for the universe. That purpose is for the existence of mankind. And that's what we're trying to show with these evidences of the fine-tuning. So now we're going to look at that. What we're going to do tonight, if we can get through it all, is we're going to look at evidence of the fine-tuning of the universe. And we're going to show just a few examples, because there's many evidences for that. And it would be impossible to do them all. But I'm going to pick out about 3. Then we're going to look at evidences of our solar system, how unique it is, and how it's so finely tuned. And these we've already mentioned last week a little bit. We're just going to go into them with a little bit more detail. Hugh Ross wrote a book called The Creator and the Cosmos. And in that book, he lists 35 different factors or parameters for the universe that must be what they are within a finely narrow range for physical life of any conceivable kind to exist. And I'm going to go through these quickly, and these are not all of them. I couldn't, too much to produce all of them, so I produced some of what I call maybe some of the more important ones. But they include things such as the strong nuclear force. That's the force that binds atoms together to form molecules, or protons and neutrons to form atoms. Then there's the weak nuclear force. There's gravitational constant. There's the electromagnetic force. And all these have numbers associated with them. They are constants. There are numbers that are associated with these forces. Then you got the ratio of electron to proton mass, the ratio of numbers of protons to electrons, the expansion rate of the universe, the entropy level of the universe, baryon and nuclear density of the universe, the velocity of light, the age of the universe, the initial uniformity of radiation, fine structured constants, average distance between galaxies, on and on and on, average distance between stars, the decay rate of protons, carbon to oxygen energy level ratio, ground state energy level of helium, polarity of water, the water molecule, very interesting. We don't know exactly all the details of why water exists in the way it exists, but if it didn't have that polarity, you and I would not be here today. The size of the relativistic dilation factor, which we talked about in here, the uncertainty magnitude of Heisenberg's uncertainty principle, which is a quantum theory concept. And these are just to name some of them. And he lists, like I said, like 35 of these things. And every single one of these has to be precisely what it is, or our universe would not exist in the fashion that it exists today to produce life. Then he goes and looks like 66 other parameters. So you got your 35, and now he looks at 66 other parameters, and this is more for the fine-tuning of the galaxy, sun, earth, moon system for life support. And these things include the moon, its stars, the galaxy must have values falling with narrowly defined ranges for life of any kind to exist. And like a lot of people in this class, Dr. Ross then tries to make this a mathematical formula. Now, do you remember the Drake equation from last week? Anybody recall that? The Drake equation was what Frank Drake and Carl Sagan came up with to estimate the amount of life that we would expect in our universe, or especially in our galaxy. But it was based upon a lot of educated guesses, and a lot of things have been discovered since the Drake equation was even written. And turns out that a lot of guesses were wrong when it comes to the Drake equation. So what Dr. Ross did, he estimates the probability of obtaining the necessary parameters for life support to be a probability for the occurrence of all 128 of these parameters, and that number comes out to a 10 to the minus 166 power, and this would be less than one chance in 10 to 144. And what that is basically a 1 in 12 trillion chance that our universe exists the way it is. That's pretty fine-tuned. I would call that on a razor's edge, would you not? And so that's what he did with his formula, and I don't know if that's exactly right. I mean, to the trillionth power. I don't know. This was his job, or his thing. And he's a believer. He's a progressive creationist. We've talked about him some in this class, but certainly he's a believer, and he may have some biases. I understand that. But scientists don't argue about these constants. The constants are what they are. And the scientists don't even argue that the constants have to be what they are. That's not their argument. We're going to talk about their argument next week, but that's not really their argument. It's just, how do you look at that? I look at it as a prima facie example of a designer. That's the way I look at it. I mentioned I failed to mention one of the constants, and one is the cosmological constant. The reason I bring that up is I'm going to talk about it in a minute. But that's another one of the constants. I didn't put that in your paper or on the slide. So what's interesting about that is, if there is less than 10 to the 144th power that life could exist in the universe if everything wasn't fine-tuned the way it was, there's only 10 to the 22nd power planets in our universe, estimated. So you got a lot less planets than you even have a chance for life to exist in the universe. I find that an interesting number, don't you? And if you don't think that's a big, big difference, it's a huge difference. 10 to the 144th is a lot less than, obviously, a chance than 10 to the 22nd, and that's the number of planets in our universe. According to Robert Collins, let's look at gravity. That's one of them we talked about. We're not going to spend a lot of time with this, but trust me, gravity has to be fine-tuned. And the interesting thing about gravity, of all the four forces that we know about in the universe, the weak force, the strong force, the electromagnetic force, and the force of gravity, by far the weakest of that is gravity. But gravity, if it wasn't what it is, we couldn't have planets today. We couldn't have a lot of things. And it has to be finely tuned. That's the point. It has to be finely tuned. It's kind of like taking a knob on a radio and turning the dial a little bit. You turn that dial just a little bit, you don't hear that radio station anymore, do you? If you're driving out in West Texas or somewhere and you're trying to find a radio station, you have to be precisely on that dial. And that's the way gravity is. If you move that dial just a little bit, either one way or the other, life would be impossible. And Robert Collins says the small adjustment of the dial would increase gravity by a billionfold. Life couldn't exist. Just a small change in that constant number alone. And that's the weakest of the forces. How about the cosmological constant? What is the cosmological constant? Cosmological constant is actually that fudge factor that Einstein talked about when he didn't realize that the universe was expanding, and so he added this fudge factor to it. Turns out there was a fudge factor and it was real, and it's called the cosmological constant. And he retracted that later, realizing that in fact the Earth is expanding. And so it has to be remarkably well adjusted in our favor, the cosmological constant. Now I know you don't know these numbers, and I get that, but I'm just trying to show you how fine-tuned everything is. First, and this is the interesting thing about the cosmological constant. When you look at it from a theoretical standpoint, it should be a very large number, but it's a very small number. Robert Collins says, fine principles say that this number should be very large, but fortunately for us, it is not. And it's widely regarded as the single greatest problem facing physics and cosmology today. We don't know why it is what it is, but it is what it is, and if it wasn't, we wouldn't be here. It is not the expected value you get, and yet that's what we got. And if we didn't, we wouldn't be here. And this is another example as far as from the universe. The difference in mass between neutrons and protons. Neutrons and protons are in the center of the atom. We know that, and depending on how many they are, that tells you what atom you're talking about, what chemical you're talking about. And there's a certain mass in between them. And an increase in mass of the proton by just 1 part in 700, nuclear fusion stops. What happens when nuclear fusion stops? You don't have stars. You don't have stars, I guess we wouldn't have life, wouldn't we? There's no way you could have life if you didn't have stars. And that's just changing it to 1 part in 700. Why is it the way it is? There's no explanation for it. It just is. And if it wasn't, we'd be in trouble. And that's true of all these constants. Why is the speed of light what it is? Don't know, but it is. And if it wasn't, we'd be in trouble. So, rare earth people did the same thing. Remember we talked about rare earth? They looked at the Drake equation and they came up with their equation. They call it the rare earth equation. So rare earth was refuting the concept of the mediocrity principle, right? That was the reason it was written. And these were not, rare earth is not written by creationists. These are scientists that don't believe in God per se. Well, they came up with their own equation. And so the rare earth equation now takes some of those guesses that Drake and Sagan looked at, and now we know the reality of some of those things, and then they put in their own equation. So they looked at the stars in the Milky Way galaxy times a fraction of the stars with planets, times the fraction of metal-rich planets, times the planets in a star's habitable zones, which we talked about, times the stars in a galactic habitable zone, times the fraction of habitable planets where life does arise, times the fraction of planets with life or complex metazoans arise, times the percentage of a lifetime of a planet that is marked by the presence of complex metazoans, times the fraction of planets with a large moon, times the fraction of the solar systems with a Jupiter-sized planets, which we'll look at that in a minute, times the fraction of planets with a critically low number of mass extinction events equals the probability that basically is zero, or approaches zero. And again, these are not creationists. So what they're saying is, outside of our Earth, the probability of life, of intelligent life developing approaches zero. That's not what the Copernican principle said, is it? It's not what it said at all. We should expect millions of planets. So let's look at now from the solar system point of view. This comes from Michael Denton, who we studied a lot in our study on evolution. He wrote a book called Nature's Destiny. And Michael Denton said, Earth's location, its size, its composition, its structure, its atmosphere, its temperature, its many intricate cycles that are essential to life, such as the carbon cycle, the oxygen cycle, the nitrogen cycle, the sodium cycle, and so on, testify to the degree to which our planet is exquisitely and precariously balanced, like on a razor's edge. We're not going to have time to go into the sodium cycle and some of these other things, but I do want to look at a few of them. So to say that these numbers seem to contradict the Copernican principle, I think would be a great understatement. Approaching zero is would be an understatement. That violates the Copernican principle. 1 and what did I say, 10 to the 144th power, or 12 trillion, 1 in 12 trillion chance, I would say that that violates the Copernican principle rather distinctly. And it certainly would be a great understatement to say they contradict them. They certainly do. Let's look real briefly then at our solar system itself. Is there something unique about our sun? Would you agree with me that we couldn't be here today if we didn't have a sun? I think we're all agreed on that. If God hadn't provided us with the sun, our sun, then we would not be here. Now, the Copernican principle says that there's nothing unique about our sun. It's just like any other star. Our sun is a star, right? Our sun is a star, so there's nothing unique about it. That's what the Copernican principle says. Turns out that's really not true. There is something unique. Let's look at a few facts about it. Contrary to the Copernican principle, the sun is not just a common star, but has properties making it unique to our planet and causing us to be habitable. First of all, our sun is a large star. It's not a small star. It's a G2 star. Has significant mass, puts it in the top 10% of stars. There's some stars that are bigger, but we're in the top 10% of stars according to astronomers. What does the sun do? Obviously, it provides chemical elements and a steady supply of energy, which in turn allows for photosynthesis. And we couldn't be here today if we weren't able to have plants and for animals to eat. So it's the source. That's where the source comes from. But it also supplies elements for life as well. We happen to rest in the circumstellar habitable zone of the sun. So there's something unique about the sun, but there's also something that's unique about the Earth in relation to the sun. If we were too close, it would be too hot, Mercury. If we were too far out, like Jupiter, would be too far out and couldn't support life. We happen to be just in that special distance from the sun to be in what's called the circumstellar habitable zone of the sun. Our sun happens to be not too big or not too small for us. If it was much bigger or much smaller, there couldn't be life on Earth. Stars too big aren't compatible with life because they change too quickly. There's too much nuclear fusion going on inside the suns and inside these stars. Hence, it would result in dramatic climatic changes. Would not allow for life with these severe, dramatic climate. If you think we have climate changes now, if we had a sun that was too large, couldn't tolerate it. This is just an example of different size of the sun, and ours is a large sun. Low mass stars, dwarf stars, are not particularly conducive for life either, as in order for planets to be able to support life, these planets then would have to be closer to the sun, right? Because these are smaller suns. And if you were too close to the suns, it would result in severe tides, making complex life difficult. We have tides, and we need tides. If we didn't have tides, we're going to talk about a little bit about that when we get to the moon. But if our tides were too dramatic, it wouldn't support life. And that's what would happen if you had a sun that was too small and a planet that needed to be close to it. So when you see dwarf stars or these huge stars out in the galaxies, they probably can't support life. And as a result of this also, water would freeze and solar flares would put out a significant amount of radiation, anywhere from 100 to 1,000 times more than our sun did. And let me just say, if our sun put out 100 times more radiation than it already puts out, we wouldn't be here either. That gives you kind of a conception of how big the sun is, how big Jupiter is. There's a brown dwarf there. The sun actually is that little white area at the very top. Then there's a low mass star, and then there's the brown dwarf star, even smaller. That's actually a brown dwarf planet. Then you got Jupiter, and then you got Earth at the very bottom there. And you get the relationship of the size of Earth to Jupiter just by that one picture alone. Our sun is highly stable, and this is very important. It only varies about 0.1% over a full sunspot cycle in 11 years. The luminosity or brightness of the sun seems to be just perfect and optimal for extracting information from its spectrum. And again, we talked about this a bit. The size of our Earth in comparison to the size of the sun is optimal. And if our Earth, not the sun now, but if our Earth was too small, we would have to be closer to the sun, and we'd be receive enough energy. And once again, this can produce something called tidal lock. And tidal lock is where the tides go in one direction. And I'm not a scientist, but apparently that's not good. If the tides only went in one direction towards the sun, it would be hard to sustain life. Here again, some more pictures. You got the sun, the moon, and Earth in between. Now, this is interesting, and this is one of the things that Privileged Planet, the book, points out. This comes from Guillermo Gonzalez and Jay Richards, which we've looked at. And they also note that the sun also serves as a handy astrophysics lab. In what way? Well, number one, it's close enough that we can study a star. We don't have to go light years away to study a star. We got a sun that's relatively close by galactic standards. So the sun's local environment seems to offer the best type of habitat for complex life, and at the same time its particular properties disclose vital scientific information more abundantly than more common types of stars, while also providing us with excellent examples of stars in general. And that's why it's good for that. It's also good because when it comes to eclipses of the sun, which we're going to look at in a minute, because of the way the sun and the moon are in relation to the size of the earth, we have total eclipses, and we'll look at that in a minute. So how about our moon? Is our moon anything special? Now, what would Copernican principle say? Well, it would say, of course not. There's nothing special about the moon. It doesn't really, we don't need it for life, or there's nothing particularly special about our particular moon. And that's not true either. Our moon also seems quite unique and allows for existence of complex life. Why? Because of its size primarily, its relation to the earth. And this comes from Peter Ward and Donald Brownlee once again from their book Rare Earth. The presence of our huge moon seems to be one of the most important and yet most perplexing. Without the large moon, the earth would have had a very unstable atmosphere, and it seems most unlikely that life could have progressed as successfully as it has. Now that last statement is an evolutionary statement. And I don't agree with that part of it, except certainly there's been progression within species, and maybe within species or kinds, it wouldn't have been as vast as it was. But you do need a big earth. Why? Because the earth helps to change the tilt of the earth. You need a big moon. And the reason is the moon helps to change the tilt of the earth. If we didn't have a tilt in our earth, it'd be hard to sustain life. If we were just straight up and down. But there's about a 22 to 23 to 24 degree tilt in our earth, depending on the time of the year and so forth. The average is about 23 degrees. And it's that tilt that allows the climates to be moderate. And we wouldn't have that tilt if it wasn't for the moon. So the influence of the Earth's axis comes from the moon. And that's very important. This tilting of the Earth turns out to be extremely important and conducive for a habitable planet. And this tilt causes lunar tides as well. And it stabilizes the Earth's spin. So that tilt allows for lunar tides, and it allows for the spin of the Earth to be what it is. If our spin of the Earth was faster than it is, that'd be much more problematic when it comes to life. If it was much slower than it is, that would be much more problematic for life, for sort of obvious reasons. You'd have areas that were just way too hot or areas way too cold. Not too much lives on Antarctic. There are life on Antarctic, but not just a whole lot. But human life could not be sustained there, at least without a whole lot of help. So this tilt causes lunar tides, and again, this slowing of the rotation of the Earth. Real important, comes from the moon. So without it, the surface of the Earth would be either extremely cold or extremely hot, making complex life unlikely. Simplistic life, maybe. Extremophiles, maybe. Complex life, no. And the degree of tilt seems to be perfect. You need about a 23, 24, 21 degree tilt. If you had a 90 degree tilt, that doesn't work either. So the amount of tilt that we have is real important. And it happens to be because of the size of the moon in relation to the Earth. And the moon, we have a big moon compared to other planets. Our moon is about a third the size of Earth. And that happens to be just right, and the distance from the Earth. Now, theirs seems to be just right. There's different theories on where the moon came from. As creationists, we know where it came from. God created it. But some say the moon actually originated as part of the Earth. And the rocks that they found on the Earth, or on the moon, supposedly helps to prove that. I could say supposedly. So it's also responsible for tides. Are tides important? Yes, tides are very important. Tides drive currents, which help regulate climate by circulating enormous amounts of heat. And without lunar tides, our world would look quite different. And this is just an example of now the sun causes tides too, but the moon influences them greatly as well. You need both. And if we didn't have these, Gonzalez and Richards say Seattle would look more like southern Siberia than the lush, temperate Emerald City it is. So we need tides. and the moon supplies them. Other benefits from the moon? It also serves as a protective barrier against bombardment from comets and meteors. Takes some of the hits for the Earth, in other words. That's pretty obvious, isn't it? You seen the moon lately? It's got a lot of craters on it, doesn't it? I mean, so it's pretty obvious. It's taken some hits. And again, we talked about its distance. The distance from the Earth and the Sun allows for inhabitants of Earth to witness periodic eclipses. Now, on the surface, that's not a big deal, is it? Periodic eclipses, I don't know of any specific benefit that it has to the Earth and making it habitable or not. But what does it do? It makes us able to discover things. Totally, and when the moon is, our moon is unique. When you have a total eclipse of the sun, it just happens to be because of the size of the moon, the size of the sun, the distance between the moon and the Earth and the moon and the sun allows for a total eclipse to occur where it just perfectly fits. Perfectly fits. It didn't have to do that. It doesn't have to be that way. But in our system, it does. And so as a result of that, we were able to verify, for example, Einstein's theory of relativity by looking at a total eclipse of the sun and looking at the starlight that was coming around it as a result. And there's other things that have been discovered because of the total eclipse too. I don't think has anybody in here ever seen a total eclipse? I don't think I have. I've seen partial eclipses. You have to be on certain parts of the Earth to see a total eclipse, but they obviously do occur. And they make discovery possible. How about Jupiter? Now, you wouldn't on the surface think that Jupiter would have anything to do with life on Earth, would you? Now, what in the world would Jupiter have to do with life on Earth? According to the rare earth authors and the privileged planet authors, and many others too, not just them, but other astrophysicists, it turns out that Jupiter may be very important to life on Earth, very important to life on Earth. Jupiter is massive. I may have messed up my figures a little bit last week, but just remember 300 times. It's about 300 times the size of the Earth. 318 to be exact. And that kind of gives you an idea of the difference in the mass there. There's Jupiter and there's the Earth. I don't think this was taken by a telescope. It might have been. I don't know. Jupiter has no surface. It's kind of a gaseous planet. And you kind of get that when you see some of the models of Jupiter as the time elapsed models of Jupiter. It's made up of mostly hydrogen and helium, which sounds like a star to me, but it's not a star. And it's so massive with so much gravity that the pressure inside Jupiter would be significantly more than the pressure on Earth. And in fact, hydrogen exists in its metallic state in Jupiter. That's amazing to me. But that's Jupiter. It's huge. And as a result, it has a huge gravitational force. Well, it's 300 times Earth's gravitational force. That just shows a little bit of a schematic of the interior of Jupiter and so forth. But the outside is gaseous. So here's by far, the cut to the chase on Jupiter. By far the most beneficial aspects of Jupiter is this cleaning out effect that it has and has had for many, many years. Stray bodies such as asteroids are affected by its strong gravitational force. And because of that, these asteroids don't hit the Earth with any significant frequency. We've had some, not I guess asteroids, but large meteorites, and there's examples of those in the Earth where those meteorites have hit. The theory behind why dinosaurs died was supposedly an asteroid hitting the Earth. But anyway, we're protected from that. And it's pretty obvious. If we were hit by a major asteroid right now, life would cease to exist. And the Jupiter seems to have a very beneficial effect. And you know what? It turns out, just like in the other things we see here, that it happens to be just the right distance and the right size to have that beneficial effect. If it was any closer, we'd be in trouble. A bit closer, Jupiter with somewhat larger mass, this beneficial effect would not have occurred, and as a result, the Earth would have been bombarded by these astronomical bodies, rendering it much smaller, the Earth I'm talking about, and hence much less compatible for life. But the same thing would exist if it was too close to the sun as well. Those are some asteroids in our solar system that are thankfully haven't hit us yet. So it also helps that Jupiter has a very stable orbit. If it didn't have a very stable orbit, this effect wouldn't be seen. And there are other planets that have been discovered in the universe that are as big as Jupiter. Because we talked about last week, we've discovered other planets besides the planets in our solar system, hundreds of them. And it turns out there are lots of other planets out there the size of Jupiter. But there's no Jupiters like we have them. They're either too far from the sun, too close to the sun. If they're too close to the sun, you'll see the term, or you'll read the term sometimes, hot Jupiters. That's what they're talking about. Jupiters are at the same size of our Jupiter. I say ours, I mean in our solar system, but too close to the sun. So no Jupiters like we have them in our solar system exist. Jupiter-sized planets mankind has discovered, again, that none of exists that would be unique like our Jupiter is. So the last thing we're going to look at, the last evidence, and then next week we'll get into the topic of why, and we won't have time to finish this because the first bell is already rung, I think. It hadn't rung. Okay, we just have about 10 minutes so. We're going to look at plate tectonics, and we won't finish that, but we will get into it since we have a little bit of time today. And then the end of the second part of the lesson next week, I'm going to look at why scientists ignore this fine-tuning. They know it exists, but they ignore it. And we're going to look at why they ignore it next week. But before we do that, one more. And again, I picked out some of my favorites, but we could have looked at some 35 or 36 of these examples. We don't have time to do that, just in our solar system alone. And this may be the most important one. And yet it's probably the one you know least about, at least if you're like me, or unless you took some special courses in college on, in geology or geophysics or whatever, you're not going to know much about plate tectonics. You kind of know about them, but you don't really know about them probably. But they're responsible for volcanoes and earthquakes and things like that. Guess what? That sounds bad, doesn't it? Sounds bad that we've got something that produces volcanoes and earthquakes on Earth. Sounds like all that is nothing but destruction. Turns out we probably wouldn't have life if that wasn't occurring. And the reason is plate tectonics. So there's two things that are unique. There's at least two things that are unique about Earth when we look at it that's completely different than any planets we've seen so far, either in our solar system or any other solar system for that matter. One is water. That's a big deal, trying to find water. And there's been, does Mars have a little bit of water? Does it not have a little bit of water? But certainly there's no planet to date that has an abundance of water. And you could say the Earth has an abundance of water. Wouldn't you say that? A lot of water. We got a lot of water. Maybe 2/3 of our planet is water. And that's real important for life, isn't it? But the second thing, and I hadn't thought about this before, but mountain ridges. We see the we see the Rocky Mountains, we see the Alpines, and all these mountain ranges that are throughout the entire world in South America and in Africa and other places. That's unique. You don't see that in any other planets. You see some volcanoes maybe in other planets, but mountain ranges like we have is unique to Earth. They're all there to cut to the chase because of plate tectonics. Plate tectonics plays an extremely important role in the habitability of the Earth in providing a sort of homeostasis between Earth's oceans and land masses. And I said this last week, but if you didn't have mountain ranges on Earth, what would you have? You would have an Earth that's nothing but water. It would be totally, completely submerged in water, making it uninhabitable for intelligent life. And so that's very important. Plate tectonics plays a role in that, in this homeostasis. And it continues to play along. If plate tectonics stopped, now it'd take a long time, but eventually you would lose the mountain ranges. And that would not be good, would it? Now again, it would take a long time. So these tectonics have to continue. And they have to continue for other reasons too, which will become important next week when we have time to look at them. So what are they? And this will probably finish it up when we look at what they are, and we'll look at the detail of the importance next week. We didn't know about plate tectonics before the early 1900s. No idea. We knew volcanoes. We knew about earthquakes, obviously, but we didn't know about plate tectonics. So it's a fairly new scientific discovery. And an American geologist by the name of Frank B. Taylor, he proposed that the drifting of continents caused the great mountain changes on Earth. That was a new concept, the idea of continents being able to drift. Have you ever heard of continental drift? Surely you have. That's plate tectonics. That hasn't been known except until Frank Taylor proposed that maybe continents do drift. And maybe this drifting of the continents is caused by these mountain changes, the mountain chains on Earth. There's a picture of the various tectonics that have been identified. We won't go into a lot of detail, but obviously there's the North American plate, the Pacific plate, African plate, Eurasian plate, Australian plate, Antarctic plate, so on and so forth. Now, since the time of Taylor, man has discovered that the uppermost layers of the Earth, known as the crust or mantle, that I should have said crust and mantle, there's the crust and the mantle right underneath it. We've known about this since the time of Taylor, and through the process of thermal convection, the continents do in essence float. It just doesn't seem that way. That's just a picture of the crust and the mantle and what goes on in the core. German meteorologist, and there's more detail in your paper that I wrote a little bit, but Alfred Wegener, he revealed the presence of enormous underwater volcanic centers, areas where the seafloor literally pulls away from itself. Plate tectonics. Continents are composed of granite and basalt, primarily, but because granite is less dense than the basalt, the granite-rich continents essentially then float on a thin bed of basalt. And the example that's been used over and over again, and you'll read about when you look at plate tectonics and the Earth in general, is think of an onion and the layers of the onion. The outer layer is obviously the crust, and on that crust are smudges. And those smudges then would be mountain ranges that we have. And then all the other layers of the Earth would be underneath that. And that's a good example of when you start thinking about plate tectonics. And I think that's a good place to stop. Next week we're going to look a little bit more detail of what plate tectonics are, since it's kind of new to me and probably new to you. And then we're going to look at why they're so important, because they are. And then after that we're going to address the subject as why scientists ignore this fine-tuning. They don't deny the fine-tuning. I want to make that real clear. I don't know of any scientist that denies the fine-tuning, but they sort of ignore it and pass it off, and we'll see why they do that next week.